Alright, so let's add a few more elements and test them. So we've added 11 here. So let's set a breakpoint and then we'll start with the debugger. So the debugger's in the top right corner. Not sure if we already did this one, but we could just do it again. So we have our linked heap, this time at memory location 953. So if we click view, we can see we have 6 and 5. So I'll just click that. The root is 5, the last node is 6, and you can see that they've written that backwards. I'm not sure why they did that. I think possibly because of the iterator. When they retrieve the elements, it can be in an order that may not be the order that you thought the order was, so it can be in a mixed order basically. So iterators can do that. They may print it out in a different order. So here we'll just check the last node, which is 6. That would be the last node that we added to the heap. Then we have our root, which is 5. Its parent is null. Its left is 6. Our right is null, and then the left we have null and null. So that's about it. So we'll step into that. We'll instantiate a new node here. Can jump in. So we're going to call the super reference carry the element to that parameter, or pass it to that parameter. It's going to pass an element, set element to the instance data to the parameter, or the global variable set equal to the parameter. Then left will be set to null and right will be set to null. Parent will be set to null as well. So we have our node here. After we click that, we should have our node. So we have we have our node at memory location 1013. We can see our nodes holding the element 11, the object. Its parent is null, its left is null, and its right is null. And remember that the heap node class has a parent object, has a parent field, and it extends binary tree, so it would also have everything a binary tree node would have, which means you can just think of them like they're connecting, even though this is extending that through inheritance. It's an easy way to think about it is just think that they're all connected together. So you have the fields here. Underneath you'll have a parent field. So you have element, left, right. So every every heap node has a parent, and it also has a binary tree node which has well, it also is a binary tree node, sorry, not has, so it has an element, a left, and a right as well. So you can think of each heap node having 4 things instead of just 1. So it contains all of that stuff, all of those fields, into one like super node. So after that node's set up, we have the element pass, all the parameters set up, so you can see that the node has, as we said, parents null, elements 11, left and right are null. Then so it's going to check if root is equal to null. Well, is root equal to null? It's not, it's currently 5. So it should skip that, go to the else, and then the first statement. So it's saying, okay, well, our heap node of type T next parent points to get next parent add. So we're looking for the parent of 11. So what's going to be the parent of 11? We're going to step in. We're going to say, okay, well, heap node of type T result points to last node. So result's going to point to 6 at memory location 989. We're just going to go by the numbers because I'm going to make them all different. We won't have any double numbers, so we won't have to go by memory location. So we'll just say the memory location at the value 6, or the integer 6. So result's going to point to 6. It's going to point to last node, and last node's pointing to 6, so it's going to point directly to 6. While result is not equal to root. So that should be true because result's not root. And result dot get parent dot get left does not equal to result. I think at this time it does, so that should be false. That does equal to result, I mean. So that line was skipped because once we do this calculation here, see result dot get parent dot get left does not equal to result. Well, it does. They're both memory location 989, I believe. See? So that would be false. So now we're here if result is not equal to root, so that should be true. So we should go proceed to this statement. Result is 6, root is 5, so they're different memory locations as well. It's just going off the memory locations, I believe. So if result dot get parent, so result dot get parent, let's see here, so result dot get parent dot get right is equal to null. That should be true. Result points to result dot get parent. There we go. This else was skipped. This one, I think, as we said, this one went with this one. I don't know why I was just writing like that. But that's okay. We got here anyway, so we'll just proceed with that. So next parent points to, they're pointing to the root. Yeah, so it does point to the root 990, so there's only one. Yeah, so that is the root. So right now have a look at our heap. So 5, we have 6. So that right spot is empty. The right subtree, the right child area, or the node is empty. It's set to null. So that's an empty spot. So we have 5, 6. We're trying to add 11, so it should look like a 5 as a root. Left child should be 6. Right child is 11. Right. So we're trying to fill that spot. Not sure. I think we're here now. Yeah. So we're here now. So we're gonna fill that spot, and then we're gonna set the parent of that node. Because right now, look, have a look. The node's parent. So there's a node we're trying to add 11 at the bottom there, highlighted in blue. Its parent should be null, and we're gonna set that parent as well. So if next parent. So before we do that, we think we have something else to do. So if next parent. Where is that? So if right down here. So if next parent, which is 5, dot get left, is equal to null. So that's false. So it should be it's looking for what spot should we fill it, what spot should we set it to. So that one should be false, so it should go to that next else right here. They're gonna say, okay, well the parent's right spot is empty, so we're gonna link it to that spot instead because it's empty. They're gonna say, okay, next parent dot set right to node, because we're gonna call, okay, we're gonna call our old tree methods. We're gonna just for the tree set right should be in binary tree node, I think. Set right. Yeah, right here. We're gonna just call those mutator methods or setters. Where were we here? So set right should be. It's not telling me. Probably because it's in the debugger mode, it's not going to show it. But it should set the right of. It should be calling that method. So this is just a tree. It's like a binary search tree, except it's a heap node, so we have access to all those methods that we're going to use to set and get and all that's the same stuff. Just has a different ordering and stuff. And it has a parent node. And also the left child is not less than the root. The left and right child are equal or greater than the root, so that's the only difference of this tree. Other than that, it has a parent, I believe. So it's the same idea, we're just saying, okay, well we're going to get next parent, which points to the parent, or in this case the root. We could have just said root.setRight to node, that would have worked. But we're saying, okay, well next parent, which is 5, set your right. Where is it? So right there, where'd it go? Next parent here. Set your right to point to the node that we're trying to add, which is 11. So we're just saying, okay, well, we're going to access our next parent. We could have called it temp, we could have called it sub, tree, subroot, any subroot maybe. Would have been better. Or current root, something like that. There's just the way that the code that I have is implemented, but you can change this to make it better. So it just says, well, next we're going to find the parent with this method. We're going to set that to an object reference variable called next parent of type heap node of type t. So we could have called that subroot, but then we're saying, okay, well, next parent. You can think of it like a subroot. In this case, it's the root. But on a farther down, in levels farther down in the tree, then it would be a subroot, not a root. Then we're going to say, okay, well, next parent, which is 5. Set your right. So just calling that like we were saying root.setRight or subroot.setRight, temp.setRight, current.setRight, temp root, current root, anything. We're just still calling that set right to set it to a node, so it's exactly the same what we did before. Set right to node, our node is 11. It's going to go into the binary tree node class, set it up with the setter. That's done. And we're going to set the parent. Parent points to node. So we say, okay, well, next parent dot set right. Then we're going to say, okay, we'll set that node, set its parent to next parent. So it's like, okay, we'll take the parent, set its right to the node, and saying, okay, we'll do the opposite, set the node, take the node and set its parent to next parent. So there, right? Nothing too hard. Just here's the linking right here. This is where the linking happens. This line and that line, and it's done. Then it's saying, okay, well, after you do that, maybe I'll try to comment here. Set parent node right. Then here we'll say, just say this is step 1. To link, or I should put it here, set parents. We haven't really used the word link, but we'll just set parents node right. Well, we're linking, right? Then here's step 2. Set nodes parent to the next parent, to that node. Or we can say next parent, just say subroot here. So set the node, set the node's parent, so the node we're trying to add, right? Up in there. Did I click something on my keyboard? Yeah, I think I did click something on my keyboard. Okay, so set nodes next. So to set nodes parent. No, I think that's wrong. Yeah, actually that's right. So set nodes parent. Set the node we're trying to add. Right. I'm not going to put that in bracket, but it's just going to say that is the node we're trying to add. Parent. Set its parent to the next parent or the subroot. And then here we're going to update. Step 3 is update the last node. Right. Step 4 mod count. Don't forget that. But these are the specific for the heap. So just remember that. And it would be the set parents node left if it was this one. We can do that here as well. We'll just put step 1 also here. Set parents nodes, set parent nodes left. Or set parents node right? That's step 1. Then step 2, and then step 3. So last node, where is it currently pointing? Last node is pointing to 6. So we want to say, okay, well, what's our, we want to change that to the node we're trying to add. So what's our current tree? We have our root, which is 5, its left is 6. Its parent is 5, right? That parent's null. So 6 is left and right are null. And then right's parent is 5, that's correct. Its parent is null. And then we're just gonna check if so that was 11. So right's, which is holding 11. Its left and right are null, so that's correct. So right now the last node is what we're trying to update somewhere here. Isn't it in this? I can see it down there, but it should be in this as well. Okay, yeah, here we go. So last node's pointing to 6. So we just added a new node. So is that the last node? It's not. It's 11 now. So we have to change it. So last node points to node. That's just a global variable, so we can just do a one-to-one assignment statement. Then we'll do a mod count plus plus. Done. If size is greater than 1, heapify add. Skip that. Step in. Now it's going to reorder the nodes if the tree is out of order. Okay, we'll say, okay, well, next points to last node. Temp points to next.get element. So we're saying, okay, well, next points to last node. Where is that? Okay, next right here. So next points to last node. So we're just going to check our last node, see if that's correct. 11, 11, right? 1, 0, 1, 3 memory location, so that's correct. Temp points to next.get element. Okay, where that's going to get pointed to, temp's going to point to 11. So while next, where's next now? So next is here. While next does not equal to root, which is 5. That's true because next does not equal to root. Memory location does not equal to this memory location. Also, this integer does not equal to that integer. but it's just comparing by memory location. We're just comparing by integer to make it a little easier. What you really want to compare is these numbers here at 990 to this number here at 1013. So you're saying, okay, well, while next is not equal to the root, so that's true, and cast is comparable to temp. So just think of it as temp dot compare to next dot get parent is less than 0. Well, is 11 less than 0? Is it going to return -1? No, it's not. It's going to return a 1. That should be false. Skip. Okay, now we're in here. We got into the internal methods. So that should have a thing that skipped, because it's checking if. So what's our tree now? Just for. Well, tree has a 5. Well, okay, I'll just do it here. I'll move this bracket up, just to try to explain if you don't understand. So we have 5 here. I have to comment it. So like 5 here, we have our 6 as left child. I'll just do it like that, and then we have our right child is 11. So it's saying, okay, well, can you check that it's in order? So it points next to last node. So it has a t temp here, empty right now at that point, pointing to null. And it's saying, okay, well, next points to last node. Next, which is an object reference variable, points to last node, which is 11. So next points to 11. Then we're going to say, okay, well, temp points to next dot get element. Temp points to next dot get element. So temp's going to point to 11, because it points to next dot get element, which is 11. And it's saying, okay, well, temp is not equal to root. So does temp equal to root? It's not. So that's true. And temp, where is it? Down here. Well, temp does not. Well, temp dot compare to next. So we're going to say, okay, well, can we just put a little bracket down here to save our spot? So we can substitute it like math, so we can go like 11 dot compare to, because that's what we said temp was. 11 dot compare to next. So we have next 11 dot get parent, which is 5 dot get element. That doesn't seem right. So next dot get parent, which is 5. Yeah, so next, which is 11, dot get parent, which is 5, dot get element, which is 5. So it's saying, okay, well, 11 dot compare to 5. Is it less than 0? It's checking if it's less than 0. What does it compare to return? It returns 1. Or sorry, returns -1, 0, or 1. So 11 dot compare to 5, that should return a +1. So it's asking, is it returning a -1? So it's false, so this whole statement gets skipped. So in our diagram, it's saying, okay, well, 11 dot compare to 5, it's checking, well, which one's bigger, which one's smaller, which one's greater than, which one's less than. So it's saying, okay, well, if it's false, then it's in the correct order already. If it was swapped like this, then it would reorder the heap. It would swap this element with, what do we say was there? It would swap this element with that element. I think then also it would check for the other ones. But at this point it didn't. because the definition of a heap is that all, I think I have the exact definition of a heap here. I'll just double check. Yeah, I think it's that the left and right child should be less in a min heap. In a min heap, a heap is a complete binary tree in which each element is less than or equal to both of its children. So each node is less than or equal to both of its children. So you want the node, the parent, we want the root, so in which each root is less than or equal to both of its children. So that's correct. This root is less than or equal to both of its children. That's the idea of a heap. So we want, if for some reason it didn't check here, but perhaps if it did, we can maybe do that now, just to check if it orders. We can come back. I think we're done with this one actually. Yeah, so we're done. We can stop that. We're gonna try to make this backwards. So we're gonna put an 11 here, a 6, and then a 5. But I think the way it does it would be that it would have already have changed 6 and, so look, let's start here, start debugging. I think it would have already swapped 6 and 11 at that point. So we're trying to get 11 as the root and 6 as the child. But I think when it's, by the time it's done, it reheapifies, then it's gonna have 6 as the root and 11 as the child. I'm not sure what happened there. Can we start debugging? So breakpoint stays the same. Am I missing a bracket? Okay, something's wrong here. Did I leave some notes where we just were? We were in linked heap. Maybe here, no. Did I take some brackets away? Getting some kind of strange error here. Unless I removed one of the brackets somewhere. Heapify add. No, it should just be one bracket and bracket for the top.